All right, hello everyone. Welcome to the second day of our 6-point SO88 lecture series. We're super excited. This will be our first beginner lecture, and we're going to go over prefix sum arrays today. So before we dive into the actual content of today, just some quick announcements. We have a piazza. Some people have been emailing me about this. So if you go on our class website, mitit.org/class/home, you should scroll down, and there should be a piazza section where you can join our piazza. We post announcements, updates, and other updates on that site, so it'd be really helpful if everybody can join that. Also, we finally have our problem set on the website. So on the same place, class/home, if you scroll all the way down, you should now see 2 problems listed on the website. These are, as a reminder, the problems you need to solve to pass the class. Because of any 5 of them throughout the 10 days, there are no deadlines, there are no due dates. As long as you solve them before the end of the class, you'll gain credits for this class. Yeah. Oh, yes, questions? No, so the end of our course. So I think the 16th is the last day for the class. Yeah, so any time before then, you'll be good. So if you go to mitit.org/class/home, I can demonstrate right now, actually. How do you exit? So if you... here is the piazza for joining, and then... Oh. Larry, are you logged in? You need to be logged in to see the problem set. So that's a common issue.
Wait, I think...
Well, if you are logged in, this should not be an issue, hopefully. If you're still experiencing difficulties, please see us after for the problem-solving session, or make a post on Piazza, and that should be good, hopefully. Yes. Cool. And also, on the same note, all of our course materials have been uploaded onto our course website. So if you go to the same page here, and you scroll down to our lectures tab, you should be able to see the slides and the recording. All right.
Where is it we can actually log in for the problems to see?
So you should have made an account yesterday with the platform, and if you just... Sorry?
Are the problems on the VJudge?
So there's 2 systems. The VJudge is for your own exercises and for winning raffle tickets. The MITIT platform is where we have our actual problem sets where you have to solve to pass the class.
Thank you.
Yes, right. Any other questions for the logistics side of things? Cool, all right. So today we're going to go over a really, really classic problem in competitive programming called the range query problems. These are problems where we have some kind of structure, usually like an array, and we want to process a huge range of things. And naively, if we try to consider every element individually every time we have a query, it would be kind of slow. Because, for example, if our query covers the entire range every single time, then we have to scan through every element every single time. The problem here, one of the most classic variants of the problem is asking you to find the sum of a given range. And we have q queries and n numbers within the array. So here's a pretty simple example. We have the array on top, 3, 2, 4, 5, 1, 1, 5, 3. So if we query the range from 2 to 4, you have 2 plus 4 plus 5 gives you 11. 5 to 6 gives you 1 plus 1. And then the rest should be pretty intuitive. As I mentioned before, if you really just brute force this problem, for each given range, you can kind of iterate from the left endpoint RL to the right endpoint R, and you add all of the elements together and accumulate them. However, this is pretty slow. Can anybody tell me what the complexity for this algorithm is, actually? Sure.
I think it will be n squared in reverse space.
Exactly. NQ, n squared, is actually on the title, I just realized. Apologies. But as I mentioned, every single query, you might have to go through the entire range again, and that could be quite slow and inefficient. Especially if you look at the original problem constraints, n and q can both be up to 2 times 10 to the 5th power. So if you have nq, the maximum that could be would be 4 times 10 to the 10th operations, and that would usually not fit under the time limit. Before we dive into prefix sum itself, here are just some range notations that we'll use for the rest of the lecture. If you have square brackets, that means that these are inclusive. So for 2 and 5, with square brackets, that is 2, 3, 4, and 5. If you use parentheses, these are exclusive. So for 3 and 7, you would exclude 3 and 7 and only have 4, 5, 6. You can also mix and match them, like 1 and 6. You exclude 6 but include 1. 1, 2, 3, 4, 5. Finally, the actual prefix sums. So to recap, we are given the problem where if you have an array of numbers, you're trying to find the sum for each query between some range like L and R. So the prefix sum array solution is that we basically construct a new array where each element, instead of its original value, is actually the sum of the entire prefix. So here in the first position, we just have 3 itself, so the prefix sum is just 3. The second one, we had 3 plus 6, which gives us 9. And we kind of construct this like iteratively. Now we have 11, then 12, we add 8, 20, add 3, 23, add 5, 28, and we add 4 to give us 32. And using this structure, we can actually answer our queries extremely efficiently in O1 to be precise. So consider the sum of elements with the indices in 2 and 6. In the original array, we would have to, if you use our brute force solution, we would have to add 2 plus 1 plus 8 plus 3 plus 5. But if we actually just use a prefix sum array, what we can do is identify the prefix 20, like the 6 elements, which is 28, and also identify the range we do not care about. If we subtract the entire prefix by the left prefix that we're trying to exclude, we can do 28 minus 9 and give us 19 as the sum. And if you do some quick math, indeed, 2 plus 1 plus 8 plus 3 plus 5 gives us 19. So why does this work? What we're effectively doing is we're trying to calculate this accumulation of things within this entire prefix. And since we only care about this one specific range from L to R, we can break it down into 2 ranges. One is the entire range from 0 to R, and one is the range from 0 to L, excluding L itself. And by subtracting them, this gives us like what we want, which is 19. However, you quickly run into implementation error if you try to implement this, which is if you try to query some elements like 0 to 4, you actually get an array out of bound. This is because when you're trying to exclude the left range, you actually have to subtract by 1 to get the effective prefix that you're trying to exclude. And in our case, if you have 0, that will give you -1, which is not a valid indexing. So a really easy trick to just kind of fix this solution is just push everything 1, shift everything to the right by 1, and we just have everything exactly the same, except we replace the first index by 0, and everything else is just 1 index now. Construction-wise, pretty simple. For the I+1 prefix, we basically take the previous prefix we already calculated, and we add our current element I, array I, to our number, and that gives us like the construction. So if you can verify 9, 3 plus 6, 11 plus 2 plus 1 gives you 12. Yeah. And this gives us the prefix sum array. Okay, so now I'll do a quick coding demo to implement this. All right, so first of all, no, we have to input. Oh, actually, let me take the inputs first. So the input format for this problem is we're first given 2 numbers, n and q, where n is the number of elements in the array, and q is the number of queries we have to answer. So first we read in n and q. You can see these things in our Piazza post if you look them up. But it's okay. So now we've written n and q, and then we have to read in the array itself. Cool. So if we print this out, we should see 8, 4 in our array that's given as input. Next up, we have to read in all of our queries. So before we even do that, let's first construct our prefix sums. Now, instead of just making the length the same length as array as we did, we have to make it 1 indexed, which means that we have to add a 1 here. And then we can do the rest as we did earlier. So for the I+1 prefix sum, we do prefix sums I plus the ith element in the array. Nice. So if we print this out, we should see 3, 5, 9, 14, etc. You can verify that this is indeed the correct prefix sums. Now, to answer each queries, we can do LR. So read in the input here. And the answer should be the prefix sums at R subtracted by the prefix sums at L minus 1. And if you print the answer here, and comment out here. Nice. We can verify this. The range from 2 to 4 is 2 plus 4 plus 5, which gives you 11. And then 5, 6, which gives you 2, 24. I hope it's correct. And then finally, for 3, 3, gives us 4. All right, this is working. So if we submit this to our vjudge here, it should hopefully, if it didn't make any mistakes, get accepted. All right, very, very simple implementation for prefix sums. So now you have this like pretty nifty tool. If you have any ranges, you basically can perform any kind of operations you want in this range. But is that actually true, or am I lying? Here's a very simple, before I dive into that, there are two implementations, Python, which is basically what I just did, and then if you're interested in C++, here's a slightly more verbose implementation in C++. So, yeah. So here are some advantages and disadvantages of using prefix sum. The advantages, it's extremely efficient. It's O1. That's like the best complexity you can hope for. It's also pretty easy to implement. All you do is just add some numbers and everything just works out. However, there are disadvantages. It doesn't support updates. So imagine if you try to like update a number in the original array. You would basically have to update every single prefix sums after that because everything is dependent on this value. Also, this only supports invertible operations, such as sums or XOR. And we'll actually encounter this problem next. So in our new problem, we're given an array of n bits, which are either 0 or 1. And we're trying to find, instead of the range sum, we want to find the range OR operation. Here we have the truth table for bitwise OR. I guess, is everybody here like somewhat comfortable with Boolean operations like OR? Cool. So we might be kind of like, I guess, tempted to do, some examples first. So if we want to query the range from 1 to 4, we would have 1, 0, 1, 0, which gives us 1. And if we want to query 7 to 8, we'll have 0 and 0, which gives us 0. So, it might be tempting to kind of like borrow the idea directly from the previous problem. For example, in our problem here, we have 0, 1, 0, 1, 1, 1, 0, 0. And okay, we try to make a prefix sum, but instead of using plus signs, we actually use ORs. So first one is 0, 0 or 0 gives us 0, or 1 gives us 1, or 0 gives us 1, or 1 gives us 1, 1, 1, 1, 1. Cool. So now say I'm interested in trying to query this range, 0, 0. Using our previous algorithms, we would find this as the right endpoint and this as the left exclusion point. So we have 1 and 1. What does that mean? Like, what can we even do with that? Unfortunately, since OR operations are not invertible, which means in our summation case, if we don't want something, we can literally just subtract it and then we're done. However, because OR, the truth table here, OR is kind of like deletes information in a sense, you cannot actually just like somehow subtract the left range and get the desired answers. I guess, does anybody here kind of see a way to, like, what are some observations we can make to simplify this problem and convert it into something we know? Oh yeah, here.
I think we can find the prefix sum from the right side and then check if the two answers are similar.
Interesting. Can you elaborate what you mean by that?
Like in this one, we tried finding it from like left, the prefix sum from the left. In the next one, what we can do is like we can find the prefix sum from the right and check if the.
I see. Yes, that's a cool idea. However, how would your algorithm handle, for example, this case? So if you do the left prefix sum, this will be 1, 1, 1, 1, 1, 1, 1. And the right side will also be 1, 1, 1, 1, 1, 1, 1. I guess what would your algorithm do in this case?
Never.
I see. Yeah, it's a hard problem, and like it takes I think creative thinking to really solve this problem. I guess before I dive into the solution, does other people have ideas? Cool. So one of the key things in competitive programming is not only you use these kind of like, oh, sorry, is there a hand? Oh, yes.
I mean, I've observed that whenever you do a OR operation with 1, it's always going to end up being a 1.
Nice observation. Any other observations we can make regarding the problem? Oh, yes.
If you take like just the normal prefix sum, then if it's positive, it's going to be value.
Exactly. Okay, spoiler alert. That is exactly what we're trying to do. So we have this problem where prefix sums does not support any non-invertible operations. However, we can make a very simple observation first. Because in the OR table, whenever you encounter a single 1, it basically like contaminates the entire range and makes everything 1, regardless of what other values are. So actually, the only possible case where the answer could be 0 is if every single number in the range is a 0. So in this case, we see that this will be a 0 because both of these things are 0 and there's no 1. Even if extended by 1, this will contaminate this and this will give us a 1. So exactly what I forgot who mentioned earlier, what we can treat this is instead of treating these as Boolean variables, we literally treat them as normal numbers. So instead of having this table, let's treat this as 0, 0, 1. 1 plus 0 gives us 0. 0 plus 1 gives us, 0 plus 1 gives us 1. 1 plus 1 gives us 2. 2 plus 1 gives us 3. 3 plus 1 gives us 4. 4, and 4. So now, if we try to query this range, 0 to 0, what we have is 4 and 4. And if you do 4 minus 4, this tells us that the number of 1s within this range is 0. And that is indeed equal to 0. All right, so what we basically did is we found a problem that is non-invertible. But we did an augmentation such that we can actually do these subtraction operations. And this is a problem we already solved in the previous problem. So yeah, that's, I guess, concludes kind of like the basics of prefix sums. There will actually be a problem in the problem set later where instead of just having single Boolean numbers, you have entire ranges like you have multiple bits for each number. So in Boolean, if you have like 1, 0, 0, 1, 1, and you have like 0, 0, 1, 1, 0, the OR of between these two numbers, and these are in base 2, would be 1, 1, 1, 0, 1. So now instead of only having 1 bit, you suddenly have like 32 bits to consider. I'll leave that up to you to solve in the problem set. Next up, I would like to welcome my other instructor, Balint, to present higher dimension PSA.
Thank you, everyone. Before I start, does anyone have any questions about one-dimensional PSA? Hello, everyone. Hello? Before I start, does anyone have any questions about one-dimensional prefix sum arrays? No? Okay. So let's get started. So in one-dimensional PSA, we just had problems about querying different ranges in a one-dimensional array. But now we are going to be given like an entire grid, and we are going to be querying rectangles in it. So the rectangles will obviously be axis aligned, because otherwise that would not be fun. And we will again use a very similar strategy. So actually, let's just go over an example, and we will again be asked for the sum. So for example, in this array, let me just draw it on the board. 11, 7, 13. So again, maybe we will have queries that ask for the sum of this rectangle, and then we just add up all of these numbers. We could again do a brute force solution where we just have a two for loops nested inside of each other that iterate over all of the values and add them up. But again, that will be quite slow and probably will not be fast enough for any problems we will try to solve. So we will again construct some kind of like a two-dimensional prefix sum array, and the way we will define this is that at like each index we will store the sum of all of the values that are like up or to the left of that position. So for example, here we have 36 because that is the sum of like this rectangle, which are like all of the values that are like either above this cell or to the left of it. And then, for example, here we have 51 because that is the sum of those shaded values. And then there we have 21. Okay. So let's say we want to do queries about computing the sum of a subrectangle. And we will again try to do them in constant time. So does anyone have an idea how we could look at a constant number of values in this prefix sum array to compute the sum of that subrectangle? Yes?
You could like the first three, subtract the first row, subtract the first numbers of the first row, first three numbers of the first row.
So like these three numbers?
Yeah, and then the column.
Like this column?
Yeah, and then add back the one.
Ah, I see. Yes, so that is, okay, and then the one we actually start with is this entire subrectangle. Okay, that is correct. That is exactly what we will do. We have already computed these four values, and there actually exists this constant time formula to find the sum of the subrectangle based on only these four values in our pre-computed prefix sum array. So the reason this works is quite similar to the one-dimensional case, and we can draw it out to see it better. So we start with this big rectangle, where like we just pick like a rectangle that naturally contains like basically the bottom right corner of the one we are interested in. And then we see that, okay, right now we are overcounting because we also included all of these values. So then we subtract the top row and the bottom row, the top row and the column on the left to like try to get rid of all of those. But then the issue we run into in the 2D case, which we didn't have in the 1D case yet, is that we have like this rectangle that was subtracted twice. So the solution is we just add it back. And now we can do two-dimensional queries in constant time. Does anyone have any questions about how to do queries? We will get to construction in a second. No questions? Okay. Okay, yes. So if we just try to implement queries right now, we would run into the same issue Alex described in the one-dimensional case, where we would sometimes try to access these values in the array when like deciding what to subtract. Now we could just have a bunch of if statements that check, oh, if we don't need to subtract anything because we're already querying something that kind of looks like a prefix, then just have an if statement not to subtract anything. But that's like a lot of effort to implement, and your code will be longer and uglier. So what we just do instead is again just basically pad our prefix sum array with zeros on the top and the left. And then one way to think about this is one indexing, but another way to think about it is also that you just have like each of the indices kind of represents like a half inclusive exclusive range of which elements it corresponds to. Okay, but maybe the indexing isn't too important just for understanding the concept at first. Anyways, so for constructing the prefix sum array, we can use something similar to how we defined queries, where we did like the inclusion exclusion, where we do like a kind of addition, subtraction, and then we add something back. So I think this is a pretty good example. So we will use this formula where to calculate this value in the prefix sum array, which corresponds to this entire rectangle. What we will do is we will take this rectangle and add this rectangle to it, but then all of these values we've double counted, so we subtract that, and then finally we add this single value to compute this larger rectangle. And like basically the reason this works is because if we just iterate from like the top left to the bottom right, like row by row or something, then we can use all of the previously computed values in the prefix sum array to help us compute the next one. Okay, yeah, and then we basically just like write two for loops that do this a bunch of times. Okay, any questions about how to construct a prefix sum array in 2 dimensions? Yes?
Can you please explain it again?
Sure. So let's say we just initialize the prefix sum array to all zeros, and we start at the top left. Like the first row is very easy to come. Is it easier to explain the? Yeah. So like the first row, what is that? Java updater. Do I just click OK?
Yeah.
Okay. Okay, like let's say we've already computed some of the values in the prefix sum array. Let's say we've already computed everything other than 74, and we want to compute this value. That corresponds to this entire rectangle, correct? Okay, so since we've already computed this 44 and this 51, the 44 corresponds to the sum of this rectangle, and that 51 corresponds to the sum of this other light blue rectangle. So we could add those together to get like most of the things in the bigger rectangle, but we will count like all of these values twice. So then we will subtract the 28. So the computation we're doing is basically going to be like 51 plus 44 minus 28, and then we add the 7 because the 7 is the actual new value that we have. And then this should get you 74, right? Because we had this rectangle plus this rectangle minus this rectangle plus that one additional value. Does that make sense?
Yeah.
Okay, yes?
Could you repeat which rectangles correspond to which numbers in the prefix?
Okay,
Like
so
44 corresponds to.
maybe I can use this diagram that I've already drawn a bunch of time. I can just point to it again. Okay, yeah, so the 44 is like this 3 by 3 rectangle that's shaded in light blue. The 51 is also shaded in light blue, and that's like the one that has the bottom right corner at this 8. And then the 28 is the one that's double counted. That's the dark blue one. And then the 74 is just like trying to get this entire thing that where the 7 is the bottom right corner. Does that make sense? Okay. Any other questions? No? Okay. Okay. So let's look at an example problem. Is this a new? Okay, whatever. So forest queries. So you're given an n by n grid that represents a map of a forest. Each square is either empty or contains a tree. I think they're indexed from like 1 to n. And you have a bunch of queries that are like how many trees are in a given rectangle.
Zoom in a little.
Can I zoom in? Comment.
Plus second.
Okay. Is this better? That's too much. Is this good? Okay. Right. So the constraints for this problem is our grid will be 1,000 by 1,000, and we are given 2 times 10 to the 5 queries. If we just try to brute force this, then should I actually try implementing? Should I just implement the brute force? I have a lot of time. Sure, yeah, why not? So if we just try to brute force this, we will see that I get time limit exceeded because it's a lot of operations. Where's the...
Yeah, that's not a lot.
This one is Yusako. I will just ignore all the stuff that's already here instead of making a new project or whatever.
My code. Fix it in post.
Oh wait, this was your code that you just typed. Fine. I can figure out how to make...
No.
I got this. New file. CSES.
Forest queries.
How I could be as
Is it fine? Forest queries. Python. Okay. Wait, the font size on this is too small because even I can't see it. Okay. Let's see. Wait, why is this zoom thing here? Is this the problem? Is this the problem? Is this the problem?
No.
No. Is this the problem?
Yes.
Okay. Right. So the input format for this problem is on the first line we have N and Q, which are just integers. So we read in one line, and then the next line, and then we have so the main input will be given as a string. So maybe the one thing that makes this not a completely trivial problem is that you have to convert the string to treat the string as a bunch of zeros and ones. So maybe I will have grid will be an array of strings. Okay, and then I will initialize. Oh wait, I want to do brute force first. Sure. Okay. So the order in which the indices are given in this problem is you have y1, x1, y2, x2. I think what that means, I hope what that means is that y1 is the row indices. So I will actually R1, C1, R2, C2. And then I like having half inclusive, exclusive ranges and also zero indexing things. So for all of the left indices, I will subtract them by 1. And then maybe I will have a variable for the result, and then I will just have 2 for loops nested inside each other to show the brute force solution first.
Excuse me, when you say
Yes.
half inclusive, exclusive, does that mean just exclude the left?
So what that means is I want it to be inclusive on the left side, exclusive on the right side. So for example, 0, 4 would be 0, 1, 2, and 3. And this is usually quite nice. This is how for loops work as well. For loops, the second value you give it is always excluded. This has some nice properties. For example, the second value minus the first value is the number of numbers in the interval. So that's usually quite nice. So let's say I will add 1 if the position in the grid is equal to star, and otherwise I will add a 0, and then I will print the result. Okay, so if I copy the input, where's the bottom? Okay. Can I still run my code from here? Okay, 3, 1, 2. The correct answer is 3, 1, 2. So that's very cool. Now, I can I do Command Tab or Alt Tab? Wait, how do I do Control Tab? I don't know how to use a Mac. Sorry about this. It's fine. I can also just wait for the Zoom thing to go away, and then just use a mouse or trackpad, even worse.
Do you want a mouse?
I'm sure it's okay. So I can try submitting to this in Python. Very sad. I can also just like open it here and try to submit outside the contest. Crazy, it works. And then hopefully I will get time limit exceeded. I do get time limit exceeded, yay! Okay, so now I will go and solve the problem properly using a prefix summary. So I will declare, first I just initialize it with like a bunch of zeros. So I make it n by 1 by n by 1. So this is how you make a 2D array in Python. Very sad, I know. Okay. And then, so I want to initialize the prefix sum array. And then for that, I will use the formula I described. So maybe I will have a value. I will just first convert the corresponding location in the grid to an integer, because obviously if I just have like a star and dot, I cannot really do addition with those. So I just convert a star to a 1, a dot to a 0, and then I can do the prefix sum array construction. So I have like the two rectangles that I am adding together. Then I subtract the overlap, and then I add back the new value. Okay? And then, since I have already converted my variables to be like 0 index but half open intervals, and my prefix sum array code is designed to work exactly very nicely with those, I can just So I take the rectangle whose bottom left corner is R2C2, and then I subtract the two like slim rectangles on the top and the left side, and then that will overcount. So then I add back the rectangle that I overcounted in the top left. And if I run my code, C1, that is a very good point. Okay, so if I run my code, I again get 312, which is again correct. So, forest queries. So I submit it, and hopefully this time it will be accepted. Okay, very cool. It is indeed accepted. So my program is correct. Slideshow is the first one. Okay. So that was all of the content for today. I think we maybe could have covered a bit more. Tomorrow will be a more advanced lecture, and we will cover some data structures that address some of the things that prefix summaries cannot do. For example, tomorrow we will have data structures that support updates, and also that support functions that are not invertible. Okay, so here is the attendance and feedback form. Yes, please fill that out. You will get tickets for the raffle, and also feedback is useful for us to improve the class. We will have the problem-solving session right after, and please, we will try to go around the room and help people. We noticed a lot of people were struggling with problem D yesterday, so make sure to ask us for help if you need it. Okay, thank you for coming to the lecture. All right.
since you have a little bit extra time, we can also address any questions about earlier in the slide. If people had questions. Yeah.
Can you understand why the solution is constant time when you have to construct the entire prefix array?
Oh. Yeah. So the idea is like this construction of the prefix array, you have to go through the entire array. So that is like n squared time. But then afterwards, once we've already constructed that, then like a single query is.
Yeah, basically the construction is linear time, but once we've constructed the data structure, then all of the queries are fast. So this is generally how data structures will work. We usually do some kind of pre-processing at the start, which might not be too cheap, but once we did that pre-processing, we can answer lots of queries very efficiently.
Yeah, so then it takes actually like four, you get only 4 values and then afterwards. So, yeah.
Wait, actually, wait. Just 2 times valid R.
I'll leave the feedback one back at them.
I want you to do
We'll release the contest right now.
Okay. Oh wait,
Yeah.
We should search into it.
oh wait, yeah, okay, I'll change the start time to 4:45 and hopefully that should work.
4:48.
So you can change. Wait, that's such a not round number.
Wait, it's already past 4:45, so you can't.
You claim it will not let me?
Wait, no, surely you can change it.
Oh, and by just do something, we mean like we still left the contest open from yesterday open. So then, if you want help solving that, we can go around like right now for that one.
I got this. Okay, day 2 is starting in 2 seconds.